Welcome to MB class. So here's a summary of Chapter 1, Real Numbers. Let's start with the keywords. Factors of a number, multiples of a number. So factor of 6. Factor of the 6 are all those numbers that divide 6. Example, 1, 2, 3, and 6. These are the factor of the 6. 1 is the smallest factor, number itself is the highest factor of the 6. Now, multiples of the 6. The multiple of the 6 are obtained by multiplying 6 with some numbers. For example, if multiply 6 with 1, we get 6. 6 multiplied with 2, 12. With 3, 18. Likewise, we can find infinite numbers of multiple of 6. Now, the fundamental theorem of arithmetic, it states that every integer greater than 1 is either a prime number itself or can be uniquely expressed as a product of the prime number. Let's see an example. 2. 2 is a prime number and 2 is greater than 1. 4. 4 is equals to 2 into 2. So it is uniquely expressed as the product of the prime number. In the same way, 12. 12 is also uniquely expressed as the product of the prime number. 2 into 2 into 3. Come to 140. In case of 140, same. We have the product of the prime 2 into 2 into 5 into 7. So this factor is always unique. Unique in the sense, in what way you try to find the factor of the 140, you will always get 2, 2, 5, and 7. This is guaranteed by the fundamental theorem of arithmetic. Now, moving to another, that is LCM and HCF. What are LCM and what are HCF? So, the best way to understand LCM and HCF is with the help of an example. Suppose we consider two numbers, 26 and 91. Factor of 26 is 2 and 13 and 91 is 7 and 13. Now, to find the HCF, HCF as the name clearly suggests the highest common factor. So if we see the factor of 26 and 19, the common number we are seeing here is 13. That means clearly the HCF is 13. Now come to LCM. In the case of LCM, what we have to do here is that we have to take the uncommon number that is 2 from 26, 7 from 91, and we have to take the common number once, that is 13. Those number which is common, we have to write it only one time. It's 13. So this gives us LCM 182. Now there's important relation between the HCF and the HCF, LCM and the numbers. It's given by HCF into LCM is always equals to the product of the number. This is the way of verifying that the LCM and HCF which you found is correct or not. If this come equal, that means your HCF and LCM is correct. For example, in this we have find out HCF is 13, LCM is 182, and the product, that is product of the number 26 into 19, that is in the both the case we are getting 2366, 2366. That means what the value of HCF and LCM is correct. This is the way of verifying the number. Now consider another example. Suppose we have the number a with the prime factor x square, y cube, and z. X, y, and z are the prime numbers. Again, b with factors x cube and y square. Now, here we how are we going to find the HCF? The HCF in this case we can find by simply taking the lowest power of the prime numbers. If we consider a and b, the factors, see the lowest power of x is 2, so x square. Lowest power of y here in a and b is y square. So the HCF will become x square y square. As z, in the case of HCF, we have to take the common number as z is along with a, so it's not taken in HCF. Now LCM. In the case of LCM, we have to take the highest power of the prime. Highest power of the prime. Try to understand highest power means in A the highest power of x is x square. In case of B is x cube. So we are taking the power from B, x cube, x cube. Again, in case of y, The highest power is in A, YQ, and Z, the uncommon term. So this is another way of finding HCF and LCM. In HCF, you have to take the lowest power of the prime number. In LCM, you have to take the highest power of the prime number along with the uncommon number. Now moving to the irrationality of a number. So before that, we need to understand the theorem. The theorem states that let P be a prime number. If P divide A square, then P divide A, where A is a positive integer. Let's understand this with an example. If we consider A square equals to 81, P equals to 3. Clearly, 81 is divided by 3, A square by P. So here we have A equals to 9. 9 is also divisible by 3, A by P. So it's universally accepted theorem. Now, to prove a number is irrational, we use the method of contradiction. What is this method of contradiction? So let's understand this with the help of an example. Suppose we'll try to prove that root 5 is an irrational number. The first thing here we need to do is that we have to consider the opposite of the given statement. So the given statement is irrational, so we'll consider it as rational. So now, on considering it rational, we will use the definition of rational number. That is root 5 equals to P by Q. P and Q are integer and HCF of P and Q equals to 1. Now, deriving logically. So we'll derive this logically that root 5 square P by Q squaring both sides. Then we get 5 P square Q square. So now Q square equals to P square by 5. So here 5 divide P square, that means that 5 divides P by theorem. Okay, so again we'll move, put P equals to 5R. 5R in place of P, 5R. So now again squaring 5 square R square, 25. Cancel, we get Q square by 5. So here also we're getting 5 divides Q square. 5 divides Q. So now we arrive to a contradiction. How contradiction? Because by this logical derivation, we are getting the HCF of PQ equals to 5. But the thing is, initially we had assumed that the HCF of PQ is 1. Here we are getting 5, here is 1. So only the one thing is possible. So which means that our our assumption is incorrect. So we can conclude from here that our assumption, what was our assumption? Assumption was rational is incorrect. So the given statement, what was the given statement? That is root 5 is irrational number is correct.